Welcome everybody. My name is Konstantinos Peppas and I work at CERT ITI. I will present a multimodal 3D human pose estimation method for human-robot collaborative applications developed under a Horizon 2020 funded research project named Collaborate. The main subject of this work is 3D human pose estimation. It is a challenging problem as there are many degrees of freedom to be estimated, such as variation in body shape, viewpoint and clothes, as well as heavy occlusions. Also, there is a lack of datasets for 3D human pose estimation, and many of them are synthetically created due to the difficulty of capturing such a ground truth dataset. Although there are numerous approaches using just RGB imaging to estimate the 3D pose of the depicted subject, their predictions live in a scale and translation normalized frame. Regarding depth ambiguity, they use assumptions to resolve it, and these make them inappropriate for robotic applications such as human-robot collaborative applications, which require the inference of human poses in absolute units. To overcome these problems, we propose a novel deep learning multimodal 3D human pose estimator that takes as input RGB-D data and achieves above state-of-the-art performance. We created a novel multimodal RGB-D dataset of a collaborative assembly task and made it publicly available. And lastly, we proposed training with task-specific datasets for boosting performance of 3D human pose estimation in collaborative tasks. The overall pipeline of our solution is as follows. The input RGB image is passed through a 2D human pose estimation network, Alphapose, which predicts the 2D human key points of the people which are in the image. The registered depth map is projected to a point cloud and then fused with the predicted 2D human poses in order to create a 3D representation. This 3D representation is a stack of voxel grids and is the input to the 3D human pose estimation network, which outputs the final 3D human key point predictions. Alphapose is used to obtain 2D human pose predictions, from which a root joint is selected, one of the neck, right hip or left hip key points, for every human. Each pose is then back projected to the closest depth value found in the registered depth map. An occupancy voxel grid is created around the 3D location of the root joint and is filled using the depth point cloud, where a voxel is 1 if more than one depth point is within the voxel or otherwise 0. Furthermore, a voxel grid around the root joint is created from each human pose key point as well, where a Gaussian function is placed on the 2D index which corresponds to the 2D location of the key point, and then repeated in the depth dimension. Finally, we stacked all these voxel grids together. Voxel Posnet is inspired by the UNet architecture and consists of 3 encoder blocks and 3 respective decoder blocks with skip connections. It is a 3D fully convolutional neural network. It takes a stack of voxel grids as input and produces a stack of voxel grids as output, where each voxel grid indicates the probability of the key point being in each voxel. Thus, the maximum of the voxel grid is considered as the predicted 3D human key point. Every encoder block consists of 2 3D convolutional layers and a 3D max pooling operation with dense connections. The decoder blocks consist of a transposed 3D convolutional layer to upsample their input, concatenated with skip connection input, except for decoder block 3, and pass it through a 3D convolutional layer. The conv upsample layers sequentially apply a 3D convolutional layer and a transposed 3D convolutional layer to the input, providing the intermediate score maps. The final output is the element-wise addition of the intermediate score maps and the output of the final decoder block. The intermediate score maps are also used for further supervision during training. Our modification of the network is located in the encoder blocks. The additions are seen here in a light red color. A squeeze excite operation is added to the output of the 3D convolutional layers, producing per channel modulation weights. These are applied to the identity of this output allowing dynamic channel-wise feature recalibration. The reduction ratio used within these squeeze-excite layers is 4. There are two datasets utilized in this work. The first one is the CMU panoptic dataset, which is a massively multi-view capture consisting of 480 VGA cameras, 31 HD cameras, and 10 Kinect V2 RGB-D sensors distributed over the surface of a geodesic sphere. More than 60 subjects participate, performing various scenarios in groups or alone. Given that we are focusing on human-robot collaborative applications, sequences that depict two subjects working cooperatively were preferred for training and testing purposes. Thus, 7,875 frames, taken from 9 camera views, were utilized as the training set, while the testing set consisted of 875 frames from the remaining camera view. Of course, 3D human pose ground truth data are provided. Besides the CMU panoptic dataset, we created a new dataset, which comprises two actors performing a collaborative task and only one viewpoint. Specifically, the two actors demonstrate the assembly of an LCD TV. The goal is to teach a robot to substitute a human in this collaborative task. The dataset was captured using an Orbe Castra, and its final size is 700 frames. It is utilized only as a testing dataset, while 1 every 10 frames was sampled and was manually annotated for evaluation purposes. In order to evaluate our models, we used mean per joint position error, which is the mean Euclidean distance between ground truth and predicted joints for each skeleton. For a set of frames, we get the average over the MPJPEs of all frames. Also, we considered important to report the percentage of bodies that were predicted out of the total ground truth bodies. In this slide, we can see the testing results on the CMU test dataset. First, allow me to elaborate on the model titles used. Voxel Posnet OP refers to the baseline implementation. The same model, but trained on the CMU dataset, is referred to as Voxel Posnet OP CMU in the second row. Then, Voxel Posnet AP CMU refers to an implementation with Alphapose and Voxel Posnet trained on the CMU dataset, and in the final row, Voxel Posnet SC AP CMU is our proposal incorporating squeeze-excite operations. So, as it was expected, training on the CMU dataset greatly improves the accuracy of the Voxel Posnet model by over 50%. Using Alphapose further reduces the error by 13%, while predicting only 1% less bodies. Squeeze-excite blocks further improve the error by 1%. Here, you can see two images with 3D human pose predictions of our method on the right, with the baseline one on the left, where the improvement is visible. Regarding the results on the SERF dataset, training the model on the CMU dataset greatly reduces the error by 59.6%, while using Alphapose further decreases the error by 11.7% and also predicts 6.3% more bodies. This points to Alphapose being more robust to diverse input. This was not as evident in the CMU test dataset, where the resolution was higher and there were multiple viewpoints. Lastly, squeeze-excite blocks further improve the error by 9.2%. It is important to note that the respective improvement in the CMU test dataset is 1%, which highlights the squeeze-excite modification's contribution to the generalization capability of the network. In conclusion, we have utilized a large-scale multi-view dataset of two people performing a collaborative task for 3D multimodal human pose estimation training and testing. We have created a novel one-view collaborative testing dataset and made it publicly available. We have improved upon the state-of-the-art by utilizing a more accurate 2D human pose estimator and incorporating squeeze and excitation blocks into the Voxel Posnet architecture. And finally, we have achieved up to 67.6% reduction in MPJPE and 6.3% increase in predicted bodies in an unseen collaborative testing dataset. Thank you for your attention.